Okay, so we have this clever way of computing prefix products. How do we define our associative operation so that we are able to link it to addition of binary denoted integers? So let's recall how we add integers and what we need. So when we add two integers, we look at the ith bit of each of them, and we also look at the carry bits that we happen to have coming from some previous positions. And our curse was that before we have these carry bits, we cannot compute the result, we cannot compute this zi and the next carry bit. And actually, it's not that important that we cannot compute zi, it's important that we were not able immediately to compute these carry bits ci plus 1. And assume that some magician gave us all the carry bits at once. So suppose that we do not have this scheme, like somebody provided us with all the carry bits, as well as the input bits for these numbers, x and y. Then we know that the output bit, zi, is independent of all the other input bits other than these xi and yi, and the carry bit ci. So imagine that we had all these x, y, and c as inputs, so that we had all these x0, y0, and c0 up to, say, xn minus 1, yn minus 1, and cn minus 1, then we would be able to compute everything simultaneously. So we just use the circuit that we had, like we do not have really C0 for the rightmost bit, so we had sigma 0, which will get us Z0. For the next triple, Y1, X1, and C1, we'll use the circuit sigma I, which will get us Z1, and so on. So we'll actually not need this chain going by the diagonal of this circuit. And this circuit would not be that deep. We'll actually have this circuit very, very shallow. The depth of this circuit would be linear. Okay, the depth of this circuit would be constant, really. Well, this would be too good to be true. So it is just the assumption that somebody gave us these carry bits for free. But we'll now try to calculate these carry bits so that we can finish the calculation of the sum of the two numbers in this constant depth layer. Let's now talk about how we can calculate these carry bits. So let's look at a column of our computation in this addition scheme. Sometimes we know that the bit ci plus 1, we know its value without even looking at the bit ci. So if we know, for instance, that xi is equal to 0 and yi is equal to 0, then what would be the output here? The output would be ci, but the carry bit ci plus 1 would be 0 definitely, because the addition of three values, out of which we have two zeros, would always fit into the output bit and will not need to carry into the next position. So in this case, we know the carry bit actually. We know that it will be equal to 0. There are other cases. So when we have two ones here, then again, independently of the carry bit ci, we know that ci plus 1 will be equal to 1. So sometimes we actually do not need to know the previous carry bit to get the value of the next carry bit, at least in these two situations, when xi and yi are both zeros or both ones. But if they are, say, 0, 1, or 1, 0, we see that if ci is 0, then there will be no carry, or the carry bit will be 0, the next carry bit will be 0. And if ci is equal to 1, then the result will not fit here, and the next carry bit will be equal to 1. Well, actually, we can say that in this situation, when we have 0 and 1, or symmetrically 1 and 0, the carry bit ci plus 1 would actually be equal to ci. So we have three distinct situations, basically. If we list the values of xi and yi, and the relation between ci and ci plus 1, we can see that if we have two zeros here, we definitely have 0 here. If we have two ones here, we definitely have 1 here. And if we have 0, 1 or 1, 0, in both of these cases, we actually have the equality between these bits. So now we have these three distinct situations. And actually, only in this case, we need to know really the previous carry bit to be able to compute the next one. So let's now encode these three situations as three abstract values. If we have this situation, we'll encode this with an abstract value of arrow to the right. If we have this situation, we'll encode this with just 1. And if we have this situation, we'll encode this with 0. So these situations are 0, 1, and arrow, so kind of pass-through. And now if we know all the pairs of input bits, like x0, y0, x1, y1, x2, y2, up to xn, yn, we know what kind of three situations we have in each of the columns of our adding scheme. For convenience, we also can introduce the carry bit C0. So C0 is the carry bit in the very rightmost column. And this, of course, is equal to 0. We do not have actual carry into that column, into the starting column. But suppose that we, for instance, have these situations for the first three such pairs. So here we have 0, here we have pass, and here we have pass as well. So this means that the carry bit C2 will be equal to the carry bit C1, right? This means that the carry bit C1 will be equal to 0. So in this way, we know that C2 will be equal to 0 as well. And if here we have pass-through as well, we know that C3 is equal to C2, so C2 will be 0 as well. So now we can say that the sequence like 0, arrow, arrow gives us the result of 0 in the last carry bit. The sequence of 0 and arrow gives us also the 0 result. The sequence of, say, 0, 1 and arrow will give us C1 equal to 0, C2 equal to 1, because in this situation C2 does not depend on the previous carry, and C3 will be equal to 1 because it is equal to the previous one, which is 1. So we can view all this situation as computing the carry bits as results of prefix products with some specially designed operation with the following multiplication table. So let's define now our operation. So we see that depending on xi and yi, we can have the next carry bit ci plus 1 equal to 0, 1, or equal to the previous carry bit. But the previous carry bit, which is ci, itself can be 0, 1, or we can have the information that it is equal to the previous carry bit. And so, if xi, yi give us the information that the next carry bit will be 0, then we know for sure that it will be 0. So in this table, we mark the value of the next carry bit of ci plus 1, depending on what ci is equal to, what information about ci we have, and what is the current combination of xi, yi. So if xi and yi are both equal to 1, then we know that carry bit Ci plus 1 will be equal to 1 anyway, independently of the previous carry bit. And if xi, yi are 0, 1, or 1, 0, we know that the Ci plus 1 carry bits will be equal to Ci. So if Ci is equal to 0, if we know this, then Ci plus 1 will be equal to 0. If Ci equals to 1, then Ci plus 1 will be equal to 1. And in the case when Ci plus 1, the only thing that we know about it is that it equals the previous carry, Ci minus 1, and we know that Ci plus 1 is equal to Ci, then the only thing that we can put here is this arrow. So now we have an operation, basically, which takes one of these three values, and produces the result. So this is actually a table of a binary operation. And we can check that this binary operation is associative. We'll not check this now, so you can do it manually, just by a short enumeration. And thus we can say that for each xi and yi, from x0, y0 through xn, yn, we produce one of three values, 0 or 1 or pass, 0, 1 or pass, 0, 1 or pass. And we know that our C0 is, this C0 is equal to 0. And now we take the products of these guys, so of these values, under this operation. And the result of these products at its prefix of length I, the result would actually be equal to Ci plus 1. And we know how to compute all these kind of prefix products together by using the parallel prefix product scheme. So now we have some problem. We have three values here, but we are only working with Boolean values because the circuits that we are building are of conjunction, disjunction, and negation. But it's not a great deal. So whenever we need to work with three values instead of two, we can just model this table, this multiplication table, by encoding. So we can encode 0 with 2 bits, 0 and 0, 1 with, say, 2 bits, 1 and 1, and pass value with 0 and 1 combination. And thus we can build a circuit which computes our operation with 2 outputs. Now these are Boolean outputs and 4 Boolean inputs. And if we, for instance, bring it to codes like 0, 0 and 0, 1, then we know that this code corresponds to our 0 value, 0, 1 corresponds to pass value. We now look in our table that 0 times pass is equal to 0. And now we can output 2 zeros. Now, if we have, for instance, 0, 1 and 0, 1, we know that the product of two such codes should be the code of the pass value again. So for this input of the circuit, we should produce this output. So anyway, we have total determinism here. We can build a table listing all possible inputs to this circuit and all the possible outputs of these two Boolean values. And now this, in this way, we are modeling three like value system, like ternary system, using everything Boolean. So we finally can use these types of circuits with this encoding to build the parallel prefix scheme. And these values themselves can be computed, of course, in constant depth and size. So again, for each combination of xi and yi, we know what it produces, 0, 1, or pass. And finally, we'll be able to compute all CIs as prefix products of this kind of expression. So in this way, we'll build this crucial layer which computes us the carry bits. So this layer, the layer which produces the carry bits, we now augment with the layer which uses these carry bits to produce the resulting values, and what would be the resulting circuit parameters. So we have the layer which computes the carries, and this layer will have size which is big O of n log n, and the depth which is big O of log n. And finally, we have a layer whose size is big O of n, but its depth is constant. So now the depth is logarithmic and the size is, well, no longer linear. So now it is of order n log n. Well, it's natural that we have some trade-off. If we like to have strictly linear size of our circuit, we'll have to very significantly sacrifice the time the circuit needs to compute the answer. So the circuit will compute the answer in linear time, will have linear depth. But if we allow ourselves to use slightly larger size and log n size, then we can employ this parallel prefix scheme and provide a circuit of just logarithmic depth. So this is an example of trade-offs in building circuits and of non-trivial using of parallel prefix computation.